Here we're going to talk about wave interference. So the wave interference occurs if two or more waves occurs at same place at same time with the same frequency. They could interact each other, and then the wave interference happens. This wave interference could be increase the wave properties, wave effect, or decrease the wave effect, or it could neutralize the wave effect. So let's consider wave interference further in next slide. Mainly, we're going to consider two types of wave interferences. First one is constructive interference, and the second one is destructive interference. For the constructive interference, if you consider these two waves here, the first one you have a wave like this, and the second wave is like this. So both of these waves have similar frequency, and one of the waves, the first one, the crest, and the second one, crest, overlaps each other. So if these two waves happens at the same place, they will reinforce the wave and it will create a increased amplitude. So you can see that this is the resultant wave, so it's increased amplitude. So here you can see increased amplitude. Amplitude, if you calculate here, so it will be, so let's say the amplitude of the first wave is A, and the amplitude of the second wave is B. So then the total amplitude of the resultant reinforced wave is equals to A plus B. So it will be addition of the amplitudes since they are plus at the crests of two waves are occurs at the same place at the same time. And in the other hand, destructive interference. So if you see the second wave set, like so here you can see the wave, first wave is like this, and the second wave is completely opposite. So that is, if you consider the crest of the first wave and the trough of the second wave occurs at the same time. So in this time, actually the effect, or the once you add these two waves, the effect will be reduced. So let's say if these numbers are similar, A amplitude, and also this is again A, so it's also, if the amplitudes are similar, the resultant wave will be 0, so you don't have any amplitude, so that is A minus A equals to 0. That's why you don't have any wave at this time. But if you have two different waves, for example, if I draw another wave with a different amplitude like this, and let's consider the amplitude of this one is B. So the resultant wave is then, so this is the middle part. So you will have smaller wave. So the height of this part equals to A minus B. So here amplitude is A in this case. So that's why you have cancelled wave. So you don't have wave. But at this time we have amplitude B and the resultant wave A minus B. So you have A minus B resultant wave. So this is destructive interference. Let's consider some examples for the wave interference. So if you consider a wave pattern created by an object which is touching the water surface in the same frequency. So here, like if you consider uh, this is the first object, and here exactly in the middle the first object, and this is the second object. I will use a different color. So this is the second object wave pattern. So the first one creates wave fronts like this, and second one create wave fronts like this. So these circles are wave fronts created by each object which touch the water. So it will create wavefronts like this. And for the second one also, it will create waterfronts, wavefronts like this. So you can make this waterfront wavefronts circular parts like this. So you can see the pattern here. So the green one, these green circles spread out with the same gap. That means the frequency and the wavelengths are same. And red one also having same frequency. So you can see the gap will be same for this. So if these two waves created by these two objects and one is out of phase with the other one, that means if crest meets with the trough of the other one, so it will create a zero amplitude area. Okay, so like if you consider these points with the black part, so that means so it will create zero amplitude area. And if you consider the other ones like where both these waves are in phase, that means the crest of the one wave overlap with the crest of the second wave, so it will show up a larger amplitude over there. That means constructive interference. So these points will be constructive interference. So you can see this. I will use a different color maybe. So this is constructive interference points. So you can see these constructive interference points. So likewise, you can see destructive interference and constructive interference in uh, the water surface pattern created over here. Okay, let's talk about the standing waves. So if you tie a rope onto a wall, one side, and the other side, if you shake up and down, so you can create a wave pattern. We know this kind of wave pattern is transverse wave, and if you keep doing this shaking up and down, so you can make a train of waves. So it will be like lots of waves traveling forward onto the wall. And if you tie this the other end really tightly, so you can't move that end. Like for example, right here, this end, if you tie it really thoroughly, so you cannot move that end. So what will happen? The wave front, the wave train you created by shaking up and down hits the wall and it will be reflected back along the rope. So we call these the waves created by you is an incident wave. So the incident wave is the initially this girl shaking her hand up and down, and this wave is the initial wave, incident wave, and after it hits this wall, it will come back as a reflected wave. So the reflected wave could be in phase. So if you consider this second picture, so you can see this red one, picture color again. So this red one is the incident wave. Incident wave goes like this towards the right, and the reflected wave is come back along in the same line, like with the same phase. We call this as in phase wave. The reflected wave is direction is towards opposite side of the incident wave. And in the second picture, you can see one is the incident wave and the reflected wave are out of phase. So when one wave's crest point meets the other wave's trough point. So you can see like these 2 points, this is the trough point of the reflected wave and this is the crest point of the incident wave. They meet each other, and like we discussed in the previous page, so these two waves adds together and it cancels out. So you cannot see any wave. So that's why you don't have any wave here. Like it's balances incident wave and reflected wave. So when you have just right conditions, you can create this kind of standing wave from this rope shaking up and down. So let's talk about standing waves more in the next slide. Okay, let's consider the same picture again. If you consider this picture here, you can see this point right here in the middle. So in this point, uh, the region is actually a displacement of the rope is 0. So we consider these points as node points. So these are node points for the first one, and second one node points is right here, and third one, this is the node point, and fourth one, the node point is here. So here you can see this displacement of these points are 0, or you can consider minimal. And on the other hand, antinodes is the maximum displacement point. So where you have maximum energy. For example, this point in the first wave, this point is a antinode point, and the same way this point is a antinode point. So antinodes here you can find like this is antinode point. Yeah, these are antinode points for the last wave pattern. So here you can see the displacement is maximum, and when you have maximum displacement, the energy will be maximum. So if you consider these nodes and antinodes, they actually occurs equally apart from each other. For example, this is antinode. Let me use a different color. So this is first antinode, and this this is a node over here, and this is another node. And if you consider antinodes, this part is one antinode, and this part is one antinode. If you see the distance between this node and antinode, it's always equally apart from each other. Okay, let's try to create a standing wave with the same way we did it in the previous slide. So one end of the rope is firmly tied to support, and the other side you're shaking your hand up and down. Then you can see the wave train is created by that one. And if you set the right frequency, you will get the standing wave. The right frequency means if you can get the node points at the same position and the antinode points at the same position, you can create a standing wave. So the first picture refers to some particular frequency. And if you shake the rope twice as the frequency like previous, if you shake the rope with the twice the frequency like you did it in the previous case, so you can see the standing wave of half wavelength. So that means you will create two loops. So if you check the figure B, so you will have this is the one loop, and this is the other loop. So you will have two loops like this. So what we did here, so this is the node point and these are antinode points. So what we did here, so we increased the frequency twice. So it created two loops. And in the same way, if you shake the rope with 3 times frequency, so you can see 3 loops. If you check the figure C, so you can see here the first loop, second loop, and third loop. So likewise, you can create loops uh, by changing the frequency. So these are some examples for standing waves. So the waves created in a guitar string or violin string refers to a standing wave. So you can find a node points and antinode points since it's fixed to two positions in each end. And if you consider a trumpet, so again you can create a standing wave over there, and trumpet or flute. So it will sound waves in sound waves create as the standing wave. So these are some examples for standing waves. Okay, let's talk about Doppler effect. Actually, this Doppler effect you all experienced in many times. For example, let's say if you are standing on the sidewalk of the road, and if the fire truck approaches you, if the siren of the fire truck, uh, if the siren is on, you can hear the frequency of uh, siren as higher frequency when it approaches towards you, and when it's past or when you move away from you, so you can see a lower frequency. So same siren, so you can hear with higher frequency and lower frequency when it's approaching towards you and moving away from you. This effect we call this as a Doppler effect. Let's try to understand this Doppler effect. So if you consider a bug, small bug, let's say it's in the middle of the quiet puddle, and if the bug is juggling its legs, and you can see it will create a wave pattern. So in this picture over here, this blue circles refers to the crests of this wave, and you can see these uh, blue circles like this. So these are the crest points. So here again, these are the crest point of this wave. So if this bug is like a moving its legs with the same frequency, so you can see this wave pattern at the distance between two crest points. Let me find this. So the distance between two crest points are similar for each case. So you can see these are similar for each case. And the wave fronts actually moving away from the bug. So if I draw this one, so the wave front moving away from the bug. So you can see like these are the wave front directions, and it's moving away from the bug. So all these concentric cycles and the distance between two crest points like shown in here. So this gap and the frequency of this bug juggling its legs are same. So that means the wave frequency and the frequency of uh, juggling legs are same. Frequency of source and frequency of wave are same in this case. Okay, let's suppose this bug is moving across the water to the right side. So you can see like this bug is moving towards the right side. Let me draw it again this way. Okay, so if this bug is moving with a speed less than the wave speed, so you can see these concentric cycles are not centered anymore. So those patterns are distorted. So you can see like one side, this part. So you can see the wave fronts are closer. So these crest points, like these circles refers to the crest points. These crest points are closer, and on the other side, the crest points are far away. So you can see these crest points are far away from each other. So that means its pattern is distorted. Let's try to explain this picture again. So we have the first picture here. It's bug is just standing still and moving its legs, and this circles refers to the wave front, so the crest point of the wave, and its wave is spreading out from the middle. And in the second picture, bug is moving towards the right with the speed less than the wave speed, and you can see one side the wave pattern is distorted, and one side you can see the crest points are closer, the other side crest points are far away. So let's see if you or the observer standing exactly at point B. So when the bug is moving towards the observer, so that part, the frequency is increased. So whoever is standing at B, B point, so the frequency is higher than the frequency of bug's juggling leg, or the wave speed, or the wave frequency. And if you consider point A right here, so if observer is at this position, so you can see the wave fronts are now far away. So that means the frequency become lower. So whoever is standing at point B have higher frequency, whoever is standing at point A have lower frequency. And this is refers to the frequency of juggling legs of this bug, or the frequency of the waves in the first picture. Higher frequency at this end, so I will put it in higher frequency, so at this lower frequency. So actually this effect is again called this as a Doppler effect. So we can consider the apparent change in frequency due to the motion of the source, or it could be receiver also. So we consider this as a Doppler effect. And if you consider the speed of the source is higher, let's say in this picture, if the bug is moving with a higher speed, right here, if it's higher speed, so the frequency of the observer at B increases, and frequency of the observer at A decreases more. So that means if you have greater speed, so the Doppler effect will be greater. Okay, now let's consider a few examples for Doppler effect. The first one is sound. Actually, I discussed this example earlier in the beginning about this uh, fire truck with a siren. So Doppler effect causes the change in the pitch of a siren. So let's say if you fire truck approaches towards you, so pitch sound higher than the normal, because sound wave the crests are closer together, and you will receive this crest more frequently. So that means you will hear higher frequency when it's approaching. So I'm talking about this part of the wave. So you can see you have more frequent wave fronts. And on the other hand, when the fire truck passes you or moving away from you, so you can hear the drop of pitch. That means lower frequency. So that means the wave fronts, uh, the wave fronts which are hearing to you are further apart. So the wave fronts are further apart in this case. So you can hear lower frequency at this end, and you can hear higher frequency when it's approaching, and lower frequency when it's uh, moving away from you. So this is one of the examples for Doppler effect. Uh, let's consider another example for Doppler effect. Actually, this is more of a application. Radar waves which uses in speed gun. For example, let's say speed gun creates, usually speed gun uses to measure the speed of a car, so it uses the radar waves. Radar wave consists with the electromagnetic waves. Those are traveling faster, very faster than the car. So once this speed gun point onto a approaching car, so it will send a radar wave, and it will hit the car, and it will bounce back, reflect from the car. And this radar gun can see the frequency difference uh, which sent out from the radar gun and which receives from the reflected waves. And by comparing this frequency change, this radar gun or the speed gun calculate the approaching speed of a car. We can see the Doppler effect also in light also. So if you consider a light source which approaches to you, so the light frequency increases, and at the same way, if light source is moving away from you, light frequency decreases. So this increasing and decreasing actually you can see as the change of the color. So if you consider electromagnetic spectrum, so let's say this is visible range of the electromagnetic spectrum. So the higher frequency is at this end. The blue end we call this as higher frequency end, and the red end we call this as low frequency end. So this is low frequency end. So the frequency increases if you going towards right. So and the yellow color is in the middle. So you can consider this is the yellow color in the middle. So if you see a star which is moving towards you, that means it should have higher frequency. So usually we can see these stars as in bluish color. That means we call this star shows a blue shift. So here, so you can see this. Let me try to find the blue color. Yeah. So you can see when the star is coming towards you, it shows the blue shift. So we call this as increasing frequency. And if star is moving away from us, so usually this star called the red shift, and you can see this as the little bit of reddish color. So you can see this as a red shift or the in a red color. So this is Doppler effect on light, and this is another example on stars. Like uh, if you consider a rapidly spinning star, one end of the star shows a red shift, the other end shows the blue shift. That means you can see two different colors of the same star if it's spinning rapidly. Now we're going to talk about Bohr waves. So this is actually an extension of Doppler effect. So if you consider a source which is moving faster than the wave it produces, so this you can see these Bohr waves. For example, if you consider this bug moving on water surface, and if the bug is moving with a greater speed, then it's jiggling its legs. So you can see this waveform changes in this way. So all these wave fronts meet at a point. So let's say like for example the speed of bug, I will say like v bug equals to the speed of waves. So then these all these waves piles up at one point. So this makes a wall of waves at this point. So this is happens due to the source is moving faster than the waves it produces. The same thing could happen when aircraft is traveling at the speed of sound. So the speed of sound is roughly 340 meters per second. And when aircraft is traveling close to this speed, so again it will build up a pile of waves at a point. So this wave crest will change the airflow over the wings. So it's when it's flying close to the speed of sound, so it's really hard to control the airplane. But if the plane is traveling faster than sound, we call this as a supersonic effect, supersonic. these supersonic airplanes are smooth. So the one reason behind is like so that no sound wave can propagate in front of the airplane, or the sound all the sound waves are behind the airplane. So the supersonic airplanes flies usually in smooth, but uh, when you fly closer to the speed of sound, it's really hard to control the uh, plane due to the airflow, due to the disruption of the airflow over the wings. For the bow waves, it usually creates a V shape by overlapping waves. If you consider this picture, so the first cycle is the first wave front, and oh, it's really distorted one. Let me draw it again. So if you consider this is the first wave, and when airplane is moving faster than speed of sound, the second wave will create something like this, still trying to propagate. And in the third one, like right here. So likewise, it will create the pattern. And if you draw the wave front, so you can see a V shape over here. So this V shape creates due to these bow waves. And this V shape is narrower if you move faster. So like if you consider if the flight is moving faster, so you can see this V shape become narrower. Okay, let's consider the complete picture again. So if you consider the first example we used, V is speed of a bug, and VW, this is speed of a wave, and in this case the speed of bug is less than uh, speed of waves, so it refers to picture A. So you can see the wave fronts are narrower on right hand side, and here the wider wave fronts. So this shows you the Doppler effect, and you have higher frequency, and here you have lower frequency. And if you consider the second picture, so the wave fronts are built up at this point, so you can see a higher crest point over here. So here the V is equals to the VW, and when VE exceeds the speed of waves, so you can see the wavefront become a bow wave, and you can see a shape of this V, it's wider V shape, so the VW is higher than V, but it's like closer to that value. But if the V exceeds greatly, V is much higher than VW, so you can see this shape of the bow wave shape become narrower. So the higher speed become narrower, the lower speed here in the picture C. So you can see it's a wider V. Now we're going to talk about shock waves. Shock waves occurs when the object is moving faster than the speed of sound. Actually, it's a three-dimensional effect of the bow wave. So in the bow wave, so we considered cycles which are uh, overlapping, and it's making a V shape. But in this case, when it's three-dimensional, so sound like spread out everywhere, like in three dimension. So this will create spheres. So you can see like it's a conical shape, spheres and overlapping, and all these supersonic craft will create a shock wave, and this shock wave reach to the ground uh, when it's moving. So let's talk about these shock waves in next slide more extensively. Like I mentioned earlier, the shock wave creates when the supersonic jet is moving faster than speed of sound. So this shock wave consists with two cones. So like if you consider the bow of the supersonic jet right here, so it will create a one V shape right here cone, and we call this as a high pressure cone, high pressure, and at the tail of this supersonic jet creates another cone over here like this. So this is usually low pressure. So if you check the graph over here, pressure, and you can see at this point you can see a peak, that is high pressure, and here you can see a dip over here, it's a low pressure. So these two cones created by the bow and the tail of the supersonic jet. And actually it's not required to have noisy to create this shock wave when it's moving. You can hear a sharp crack when the shock wave sweeps behind the supersonic aircraft. So we call this sharp crack as a sonic boom. So this sharp crack or the sonic boom happens due to the intensity difference between overpressure and underpressure uh, between the two cones of the shock waves. So it happens when it's breaking the sound barrier, and also you can see this is a nice picture over here. So this is a supersonic bullet, uh, photograph of a supersonic bullet. So you can see the bullet over here, and you can see these two cone shapes. So this is from the front of the bullet, and the other cone is from the uh, back or the tip end of the bullet. So this is a nice picture of cone shape shock wave. And there are another examples like a crack of a circus whip. Also, you can hear a sharp crack. So it's again uh, due to the sonic boom effect. The shockwave and the resulting sonic boom sweep continuously behind the aircraft, which is traveling faster than sound. So, for example, if you consider this picture here, so person A, he already encountered the sonic boom, and at this point, his cone is exactly on top of person B. So he is now experiencing the sonic boom, but person C here, he's not experienced or he's not encountered the shock wave yet. So he didn't hear the sonic boom yet. Okay, let's consider a few examples for shock waves and sonic boom. Uh, Supersonic bullet passing overhead produces a crack, which is a small sonic boom. And like I mentioned earlier, the lion tamer cracks a circus whip, and this cracking sound actually it's created due to the uh, sonic boom and from the tip of the whip, as well as like if you snap a towel, and it could exceed the speed of sound and could produce a mini sonic boom. But if you consider all these objects, bullet, whip, or towel, they are not like sound sources. But when they exceeding the speed of sound or the supersonic speed, it will create a wave of air, and the pressure difference and it will make that sound of the sonic boom.